Hello, Chem 201 Organickers. Hopefully everything is going okay. I've been monitoring discussions in the course, and it seems like people are finding that the homework assignments are pretty time consuming. That's typical in chemistry, especially in organic chemistry. As I mentioned before, the learning curve in organic chemistry is really steep. Unlike Gen Chem 1 and 2, we really haven't been exposed to a lot of these ideas. So it takes some time to sort of put everything together. So don't lose heart, just do the best you can, and we will have a really productive semester. So today I want to talk about chapter 4, which are alkenes and alkynes. So let's get started with that topic. Okay. So alkenes and alkynes are considered to be unsaturated hydrocarbons. So this unsaturated piece means I have one or more carbon-carbon double or triple bonds, or I could have a benzene-like ring. This alkene, and I want you to notice the suffix, the ene, that means I have at least one carbon-carbon double bond. And notice my general formula is going to be different from the alkane general formula. Alkane was CnH2n plus 2, but those additional 2 hydrogens were lost in an alkene because I've removed those hydrogens to form a multiple bond. Alkynes contain at least one carbon-carbon triple bond. And again, since I'm losing another pair of hydrogens, I have a different overall general formula, which is CnH2n minus 2. So you're looking for the presence of these double or triple carbon-carbon bonds. And notice these suffixes are actually indicating through the naming what type of bonding in carbon is actually occurring. These benzene-like rings, we have an entire chapter devoted to those, but those are called arenes. They might be called aromatic compounds. Those have this benzene-like ring, which has this hexagon with alternating double and single bonds. And it happens to look like this in terms of its molecular structure, and it's sort of a flat kind of carbon system. Because if you notice, all of these carbons are sp2 hybridized, and they all lie in the same plane. So all of these atoms in this molecule are in the same plane, and they're actually planar or flat. We're not really going to discuss benzene and the derivatives of benzene until chapter 9, but we do show different types of structural formulas of compounds that contain a phenyl group before that. So the phenyl group is not something reactive under any of the questions or any of the conditions we describe in the chapters that we cover on, before we get to chapter 9. But you do have to know what this phenyl group looks like as a substituent. So benzene is the actual compound. Phenyl is when this benzene ring is a substituent. So this is connected to something else. And these are going to be alternative representations for the phenyl group. You might see it written out completely or just with the C6H5 molecular formula fragment, or just this capital P little h, which indicates phenyl. So be on the lookout for that. The structure of alkenes is predicted by the Vesper model to have sp2 hybridized carbons and bond angles of 120 degrees about each carbon of the double bond. So this carbon is going to be sp2. This carbon is going to be sp2. The bond angle, right, these are trigonal planar carbon atoms. So the bond angle is going to vary a little bit depending on substituents. This is a larger group than hydrogen, so it's going to take up a little bit more space, which is why you see that bond angle increasing a little bit. But all of these carbon-carbon double bonds have this sp2 trigonal planar geometry. According to the hybridization theory, right, valence bond theory and orbital overlap models, my double bond is going to consist of one sigma bond, which result from that head-to-head overlap of those hybridized orbitals, and then one pi bond, which is going to be that sideways overlap of those unhybridized 2p orbitals. Remember, I have restricted rotation, because if I actually twist the bond, if I try to rotate that bond, I break the bond. So I can actually lock the geometry around this double bond in place by having this double bond present. As such, just like we talked about in cycloalkanes, alkenes can exhibit something called cis-trans isomerism. This is because of that restricted rotation. So I could have two groups that are on the same side of the double bond. That would correspond to the cis isomer. Or I could have two groups on opposite sides of the double bond, and that would be the trans isomer. The trans alkene is going to be more stable than the cis, and that's because I have less steric interaction between those alkyl groups. This group and this group have more room. Here, I have some crowding when I put those two together. Notice that the melting point and boiling point of each of these compounds is different because they're true isomers. They have the same molecular formula. They have the same connectivity of atoms. It's their positioning in three-dimensional space that is different. But because they're locked into place because of that double bond, I can actually isolate and characterize the cis and the trans compounds. They're different compounds with different physical properties. So when I have the cis isomer, the two groups are on the same side of the double bond. Here I have this group on the same side. In the trans isomer, they are on opposite sides. So here's my double bond. I have one above and one below, or it's kind of a flat system because of the sp2 carbons, because all these atoms are in the same plane. But you can tell that they're on opposite sides of the double bond. Now, this type of isomerism is possible whenever I have two different substituent groups on each of its ends. If I have two groups that are the same, bonded to the same carbon of a double bond. This cis-trans isomerization is not possible. This is an example of that. These compounds here, even though I draw them and I'm highlighting different hydrogens, right? This hydrogen and this hydrogen are different. One is on the same side as the ethyl group, one is on the same side of the methyl group. But I can't tell which one is which. Is the hydrogen trans to the methyl, trans to the ethyl, cis to the methyl, cis to the methyl? These compounds are identical because that carbon here has two hydrogen attached. Because I can't tell which hydrogen is cis to what, I don't have that level of detail in the structure, there is no cis-trans isomerization, right? And the hydrogen, this hydrogen and this hydrogen are equivalent, so I don't have any difference, and both of these structures are equivalent to each other. If you made a model, you could tell that those two hydrogens are indistinguishable from one another. So there is no cis-trans isomerism when I have two of the same groups attached to the same carbon of a double bond. Notice these compounds are not identical because neither carbon of the double bond has two identicals groups attached. This is same side, which would be cis, and this is opposite side, which would be trans. So you want to make sure you can recognize whether cis-trans isomerism is actually occurring, because in the homework problems and on tests and quizzes, that will be a question that is frequently asked. So how do I name these guys? Well, I'm going to use this ENE in order to show the presence of that carbon-carbon double bond. You're going to notice that once I get the alkane name nomenclature system down, that anytime we add a functional group, we're actually expanding on what we already know. So the procedure for naming an alkene is very similar to naming an alkane. We just have to indicate how we're going to deal with that double bond that's present. So I'm still going to number the longest continuous parent chain in order to give the first carbon encountered of the double bond the lower number. Now, the carbon-carbon double bond must be part of the longest parent chain. So if my longest chain does not include the carbon-carbon double bond, it's not the parent. I could have situations where the longest continuously connected carbon chain doesn't include the carbon-carbon double bond, but the double bond has priority over single bonds, so I have to include the carbon-carbon double bond as my parent compound. You're going to follow IUPAC rules for numbering and naming my substituents. And if I have a cycloalkene, the numbering of the atom's ring must begin with the two carbons of the double bond. So if I have cyclohexene, this and this must be the first two carbons. The double bond must be the first two carbons. So here's some examples. I'm going to number from this direction because I need to give this carbon, which is the first carbon of the double bond, the lowest number. So that means I have hexene, because I have 6 carbons, right? So this part is because I have 6 carbons. This part is because I have the double bond. in this part is because it's carbon and hydrogen. It's a hydrocarbon. This gives me the location of the double bond. I'm indicating one carbon. It starts on carbon 1 and ends on carbon 2. I don't have to do 1-2 or anything like that. The number that I give here is going to be the first carbon of the double bond that's encountered in the parent chain. So here, again, the double bond starts at number 1. I have a hexene derivative. The ENE is indicating the double bond. This is the location of the double bond. And this is going to be on the 4th carbon. I have a methyl group. So it's 4-methyl-1-hexene. You might also see this as 4-methyl hex-1-ene. Both of those types of numbering are okay in terms of the IUPAC system. Again, this here, actually, this guy here is going to give me a longer carbon chain, 1, 2, 3, 4, 5, 6. But it doesn't include this double bond. So that is not the longest carbon chain. The longest carbon chain must include the double bond. So it's going to be that 5 carbon. So this is going to be a pentene derivative. And this is carbon 1. So it's going to be a -1-pentene. Again, I have 2 substituents now. I've got the substituent here, which is the ethyl, and the substituent there, which is the methyl. E comes before M, so I end up with 2-ethyl-3-methyl-1-pentene. I could also write that as a pent-1-ene derivative as well. That's also unacceptable. So everything else comes, and then at the end I'd have pent-1-ene. Cycloalkenes are very common. The doubly bonded carbon atoms in substituted cycloalkenes have to be, that double bond has to be the 1 and the 2. So I want to give the first substituent the next lowest possible number. So if I have this compound, I could do 1, 2, 3, 4, 5, and my substituent, which is methyl, would be on my 5 carbon. Or I can do 1, 2, 3, 4. 4 is lower than 5, so that numbering is correct. So this would be 4-methyl cyclohexene. Notice I do not have to give a location of that double bond. And that's because the first carbon is going to be 1 and the second carbon is going to be 2. So I do not have to actually indicate the positioning when it's a cycloalkene. Alkynes have a carbon-carbon triple bond. Remember, my triple bond consists of 1 sigma bond, which is my head-to-head overlap of my sp hybrid orbitals. This is going to be that head-to-head overlap. And then I have 2 pi bonds, which is that sideways parallel overlap in those 2 sets of parallel 2p orbitals. So this is what it's going to look like in terms of a molecular model. The IUPAC nomenclature for an alkyne is almost identical to that we just described for an alkene. I'm going to use that YNE to show that I have a carbon-carbon triple bond. I'm going to number the parent chain to give the first carbon of the triple bond the lowest number, and my parent must include the triple bond. So here's an example. It's written out in sort of this condensed and this line structure. I'm going to start numbering here because that's the lowest numbering. Otherwise, it would be 1, 2, 3, 4. That's not correct because the 1 and 2 carbon, or the 2 carbons, remember this is a carbon, this is a carbon, they have to be given the lowest number. And then again, this would be a butene with that 4 carbon. Again, I'm positioning the location of the triple bond. And then this is the location and the name of the substituent. Here, again, it doesn't matter that I encounter a substituent first on this direction. If I go here, I go 1, 2, 3, 4. The first carbon of the triple bond would be on carbon number 4 of the parent chain. If I do it this way, I have 1, 2, 3. So this naming or this numbering is correct. And then my substituents would be 2 methyl groups on the 6 carbons. So these would be my 6,6 dimethyl substituents. So my carbon is between 3 and 4. So the overall name would be 6, 6. Remember, I have to get the number for both of those methyl groups, even though they're on the same carbon. Dimethyl, this is the location of the start of the triple bond. I have 7 carbons in my longest chain that contains the triple bond, so that's going to be a heptyne. Go through these, make sure you understand how we correlate the name with the structure. Again, the ENE is because I have a double bond. I have to number the double bond and give it the lowest number, so I start from this end and go that way. There are no substituents there. This is the location of that double bond. So that would be 1-pentene. Same thing with this guy. I'm going to number in that direction because that means the first carbon gets the lower number. There are no substituents, and my parent chain has 6. So this is the location of my triple bond. This is indicating I have a triple, the YNE, and then that hex means I have 6 carbons. When I do have substituents, remember, I still follow the same rules. So my numbering is going to go this way. I start with carbon 1. Carbon 2 is the first carbon I encounter of the double bond. On carbon 3, I have this propyl group. Now notice this propyl here in red and this propyl are actually equivalent. It does not matter if I number this way or I number this way, because I get the same result in this case. This isomer, because I have propyl and propyl attached to this carbon, has no cis or trans isomerism. So make sure that that's also a factor. If I have a double bond and I have the possibility of cis and trans isomerism, if the isomer is indicated structurally, which means I can clearly see that those 2 substituents on the double bond are cis or trans to each other, then I have to include it in the name, or you'll get half of the points off on the exercise. Again, I have a methyl substituent on carbon number 7. This is the name of the substituent. the first carbon of the triple bond. This is the location of the triple bond. I have 8 carbons in my parent, and my ending is YNE because I have a triple bond. Here, 2-ethyl-. Now notice this, I have 1,3-butadiene. This diene means I have 2 double bonds. I'm going to number in this direction because that gives me carbon number 1, carbon number 2. This substituent is on the lowest carbon number. If I were going to go 1, 2, 3, that ethyl substituent would be a 3, and that's not correct. If I have a tie, remember, I want to number so that the first encountered substituent gets the lowest number. So that's why I have to go in this direction here for my numbering. This is going to be that 4-methyl cyclohexane. If I number 1, 2, 3, 4, 5, I get a larger number for the substituent. So that's not the direction that I number. Instead, it's going to be 1, 2, 3, 4. And it's going to be 4-methyl. And then notice I just incorporate the cyclohexane, and I don't need to give a location for the double bond because it's a cyclo and it's assumed to be carbon 1 and 2 that forms the double bond. Now, just to give you headaches, there are, again, a common name system for alkenes and alkynes. These common name systems are actually used extensively in the field. So if you were a practicing organic chemist, you would be responsible for knowing these various common names. For historical reasons, we still use them because they're just so ingrained in the nomenclature and the terminology that it's harder to actually do the correct thing and go by IUPAC. It's easier to use this historical common name. So one of these common names is ethylene. That is a name that doesn't fit, right? This should be ethene, but another acceptable IUPAC name is ethylene. The 3-carbon alkene, which is propene. So if I have this, that would be propene, and that's usually called propylene. The 4-carbon diene, which is 1,3-butadiene. So I have 1, 2, 3, and then I have 1, 2-methyl. This is actually called isoprene. I'm drawing these pretty sort of haphazardly. So when you go through these slides, just make sure you understand what it is that I'm talking about. Now, the simplest alkyne should be known as ethyne, but this is called acetylene. An acetylene torch, which is commonly used in welding and things like that, is ethyne. But again, you're never going to hear people call this 2-carbon triple bond compound by the name ethyne. It's almost always referred to as acetylene. So here's those structures. On the top row, I have the IUPAC name. On the bottom row, I have the common name. So these are names that you should at least be familiar with, especially acetylene because we talk about that a lot later. And the book, the industry will say, start with acetylene and then make this. So this is definitely one that you have to be aware of in terms of what structure acetylene corresponds to. A lot of these other ones, ethylene is probably worth knowing, and propylene is probably worth knowing. Mainly though, you do have to just realize that there are differences sometimes between how these simpler compounds are referred to in the field, in the industry. Sometimes they're more commonly referred to by their common name than their standardized IUPAC name. So you have to be aware, and you have to sort of know some of the more common ones. Now, let's look again at the cis-trans system. The configuration is going to be determined by the orientation of the atoms in the main chain. So this is a hexene. If I look at the numbering, I have 1, 2, 3, 4, 5, 6. My longest continuously connected chain that includes the carbon-carbon double bond is the 6-carbon hexene, because I have that double bond. This is the location of the double bond. This tells me that this substituent and this substituent are on opposite sides of each other. This is the same type of situation here. I have 1, 2, 3, 4, 5, and then I have a methyl group. So let's look at this and draw it out a little bit so you can sort of see where we're coming from there. So this is carbon 1, 2, 3, 4. This could be 5. This one could also be 5. Those are equivalent methyl groups. They're the same. Remember, I can rotate those single bonds so they can sort of, they're equivalent from one another. The important part is, here's my double bond. I have 5 carbons. My location of the double bond is 2. I have a methyl group on carbon 3 and a methyl group on carbon 4. That's where I get the dimethyl, and then the 3,4 is referring to that dimethyl. But notice that my chains of my chain of the continuous chain, right, is on the same side. So this methyl up here is not the cis-trans component. I have to look at the carbon chain in general, and then is it cis or trans to each other? So again, here, this is the continuous carbon chain. Here, it does this bend, and this is just a substituent. So that's not part of the cis-trans nomenclature in those cases. Now, many times I have not just di-substituted alkenes. These are di-substituted. On the carbon-carbon double bond, I have 1 substituent, 2 substituent, and then I have hydrogens. So these are called di-substituted alkenes. These you can use when it's appropriate, the cis and trans nomenclature. If I have a tri-substituted, substituted, or a tetra-substituted alkene, that's when I would use this EZ configuration. So there's some rules for how I assign an E or a Z configuration, which tells me what the geometry is around that double bond. So the first thing I'm going to do is look at the substituents on each carbon of the double bond. Here is carbon 1. I am going to look at the substituents that are attached to that carbon. This one is determined to be higher priority. And then I'm going to look at the 2 substituents on this carbon. So this is going to be carbon number 2. This is the higher substituent. This is the Z isomer. If the groups of higher priority are on the same side of the double bond, I'm going to call this Z, which means it's German for zusammen, which means together. Now, if I do the same analysis on this next carbon, I look at this carbon and I assign priority between the 2 substituents that are attached to that carbon. And I determine that this is higher. And then I'm going to assign priority on this other carbon of the carbon-carbon double bond. And what I'm going to do is assign priority between the 2 substituents on that second carbon. Now, if I have a situation, right, this is higher, the 2 higher priority groups, so the groups of higher priority are on opposite sides. Oh, this is going to be the E, because this is actually from the German one, entgegen, which means opposite. So how do I assign priority? The Z is together on the same side. The E isomer is opposite. The higher priority substituents are on opposite sides of the double bond. So how do I assign priority on those substituents? The first rule is that priority is based on atomic number. The higher the atomic number, the higher the priority. So you're going to use the periodic table. Hydrogen is atomic number 1. Carbon is atomic number 6. Nitrogen is atomic number 7. Oxygen is atomic number 8. Sulfur is atomic number 16. Chlorine is atomic number 17. Bromine is atomic number 35. And iodine is atomic number 53. So any of these substituents, the atom that's directly attached to the double bond is where I'm looking initially. The atom that has the higher atomic number is going to have the higher priority. If I cannot assign priority on the atoms that are bonded directly to the double bond, I'm going to go to the next set of atoms and I'm going to keep going until I find what's called the first point of difference. So here I'm looking at, all right, this carbon, here's my substituent, right? I have carbon, 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 carbon attached to whatever compound, that double bond that I'm looking at. Well, then I'm going to go out and look at the second atom that's attached. And I'm going to keep going if I have ties until I get to the first point of difference. If they're both identical substituents, I don't have this problem, right? Because I'm not going to have E or Z or cis or trans if I have 2 identical substituents to the same. So I will find a first point of difference if I need to designate the priority. All right, any atoms that participate in a double or a triple bond are considered to be bonded to an equivalent number of similar atoms by a single bond. So this carbon right there is said to be bonded. This carbon is bonded to whatever that carbon is, but I'm going to go this way. So if I look, here's my substituent. I have a hydrogen, and then I have a carbon. If I want to figure out the priority, this carbon has a hydrogen and then 2 carbons because this is a double bond to the carbon. So this is going to be designated by this sort of a scheme. If I have this and I look at this carbon, I have a hydrogen and I have 2 oxygens. So that is going to be how I consider the priority of that group. So here's some example. Name each alkane by the EZ system and specify its configuration. So the first thing I'm going to do is look for the longest chain that contains the double bond. So I'm going to look at this chain, and then I'm going to number to give the double bond the lowest number. So that would be 1, 2, 3, 4, 5. So my substituents are going to be the methyl, and the chloro. I also have to determine priority. So on this carbon, on that green carbon, I have a CH2 and a chlorine, and I have a CH3. This has got higher priority, so this is the higher priority that's attached to this carbon. When I look at this carbon, right, I have a methyl group and I have an ethyl group. Well, this is a carbon with 3 hydrogens. This is a carbon with 2 hydrogens and another carbon. So this is going to have priority. So this is priority. Those are on opposite sides, right? They're opposite sides. So the full name is going to be 1-chloro, 2,3-dimethyl or actually I was going to do it the other way, but I'll do it the more common way. 2-pentene. And then because they're on opposite sides, it's going to be E. So that is the name for that guy. Let's look at this next one. My longest chain is going to be here. And then I have a methyl group and a hydrogen, or I have a chlorine and a bromine. So if I compare the groups on this one, bromine is higher priority than chlorine because it has a higher atomic number. And methyl is higher priority than hydrogen because carbon has a higher atomic number. So this is going to be same side. It's going to be Z dash And then I'm going to have one chloro, no, B comes before C. I'm going to have one bromo, bleh. One chloro, one pentene, propene. I don't know, it's late at night and I'm getting tired. One propene. Does that make sense? So that's how I name this guy. In this consideration, this number C, I'm going to find the longest continuous connected chain that has a double bond. I'm going to count to give the double bond the lowest number. I'm going to look at my substituents. I have a methyl, and a methyl. And then I'm going to look at priority. So if I look at this carbon, I have a 1 carbon methyl versus a 1, 2, 3 propyl. So this is going to be higher priority. On this carbon, I have a 1 carbon methyl or an ethyl, so this is higher priority. So to name this, that's opposite, so it's going to be E. Then I have on my 2, 3, 4, I have 2, 3, 4 trimethyl. 1, 2, 3, 3 heptene. Are you guys getting the hang of this? Here, my longest continuous carbon chain is that includes the double bond, is going to be here. I'm going to name this as a cyclopentyl substituent. So I have 1, 2, 3, 4, 5, 6, 7. My priority is going to be, this is priority, because I'm looking at the hydrogen versus the propyl. Oops, I was wrong about that. This is priority because it's got the 5 carbon chain. So that's going to be priority over, or the 5 carbon cycle over the 2. So I'm going to name this guy, my opposite side is going to be E. And then it's going to be 3 cyclopentyl 3 heptene. When I have cyclic structures, the configuration of the double bond has to be cis if I have ring sizes between 3 and 7 carbons. These rings are not large enough to accommodate a trans double bond. But when I get to 8 and greater, I can have a trans double bond within the ring. So here's trans cyclohexane, where I can see those 2 hydrogens are on opposite sides, whereas this is going to be the cis, cyclooctane because of that. I can't have that in any ring size, again, in any ring size between 3 and 7, because I just cannot accommodate that strain. That trans double bond is really kinking the ring. And when I get to 8, it's pretty strained, much less anything lower. So anything between, any cycloalkene between 3 and 7 carbons will automatically be cis. If I have multiple double bonds, if I have 2, I call it a diene. If I have 3, I call it a triene. If I have more than 3, it's going to be a polyene. So there are formulas. If I have an alkene that has N carbon-carbon double bonds, and each one of those double bonds can show cis-trans isomerism, I should be able to draw 2 to the nth cis-trans isomers. So for example, if I look at 2,4-heptadiene, I could have at the carbon bond between 2 and 3, I could have trans, trans, cis, or cis. And then the combination here between 4 and 5, I could have trans, cis, trans, and cis. That gives me those 4, 2 to the second. I'm going to have 4 different isomers, 2 of which are drawn here. Notice I'm going to indicate trans, trans, because this double bond is trans, this double bond is trans. And then I'm going to locate the double bonds with the numbers. But now since I have 2 double bonds, I have to have 2 numbers. And then this would be trans cis, because this guy is cis and this guy is trans. Again, I have different geometries about the double bond, so I have to give it different names. So this trans cis is a separate isomer. It has its own physical properties compared to this trans trans. And then I have the other 2 that I didn't even draw. This is vitamin A. It has 5 carbon-carbon double bonds, and 4 of them can show cis-trans isomerism. So that would be 2 to the 4th isomers that I can possibly draw if I look at all the combinations of the cis-trans possibilities. Interestingly enough, the biologically active vitamin A is the all-trans isomer. We're going to see this a lot. In nature, even though mathematically the structure that we indicate could have a bazillion different isomers, biology is extremely selective. And what I find is that typically I might be able to have a whole gazillion bunch of isomers, but only one is biologically active. And we'll explain that a lot more later. Oh, bless me. This is vitamin A, which is retinol. This is an alcohol. But that alcohol group can actually get converted into an aldehyde by oxidation, which is enzyme catalyzed oxidation. So this is actually an aldehyde, and that's called retinal. One more thing to finish off this chapter, just like alkanes, alkenes and alkynes are nonpolar. The only attractive force is London dispersion forces. Their physical properties are very similar to those of alkanes that have the same carbon skeletons. Because of that, they also have the same property where they're insoluble in water, but they're soluble in non-polar organic liquids. They also are less dense than water, so they tend to float on water. So their properties are very similar to alkanes. They're flammable, generally non-toxic. Alkenes can display cis and trans isomerism if the doubly bonded carbon atom has different substituents. Here's the major difference between alkenes and alkynes. Alkenes and alkynes, the double bond and the triple bond are chemically reactive. We're going to look at reactions that occur with the double and the triple bond. So this is the major difference between the properties of alkenes and alkynes and the properties of alkanes. All right. The next part of chapter 4, we're going to come back to. after we discuss chapter 2, which is acids and bases in terms of organic chemistry. So with this, we're going to be done with chapter 4 for the moment until after we finish chapter 2. So that's the end of the lecture on chapter 4. I'm sure you're very happy about that. I know I am. So let's end, and I'll see you soon.